Okay, let's quickly get settled down. People at the back, can you guys hear me? Yay! I feel, I don't know if it's like people always sit at the back because they're like, oh, we got to test whether we can hear it at the back, so you know. Okay, let's sit down. Let's quickly get settled. Hopefully this Wednesday will be slightly less rushed than last Wednesday. Let's begin. Are you guys ready to learn some algorithms? Woo! Yay! Wait, why are you guys clapping? Chill. Okay, so to sort of like do a quick recap, on Monday we talked about binary search, right? Which is probably like a concept that hopefully you guys are familiar with. We also talked about big O analysis, big O notation, as well as like our model of computation, right? Bit of housekeeping before we begin, right? So problem set 2, this was released on Monday. Hopefully you know this, right? It's due Sunday night. Don't forget to click finalize when done. Actually, I think like the most common issue I've seen is not that people forget, but more like the other way around where they preemptively click on it. But remember, final means final, yeah? Now, some things to mention. So again, if you have questions, I think some of you are already doing this. This is great, right? Post on cosmology, right? I think like the problem set is trying to get you to think carefully about the different possible inputs as well, so please do that. This is something that's very common with algorithms. Sometimes it'll be like, special edge cases or inputs that you have to consider for your algorithm, right? You'll see more of this as you go on throughout the semester, right? You want to think about strange corner cases. We'll see some corners today. Not corner cases maybe, but we'll see, right? One more thing, private test cases. Some of you have been asking your TAs or your tutors, right? Can we please see the private test cases? I don't know why I'm failing. Private test cases are private for a reason. They're not private in the sense that, oh, if you ask, we will give it, right? These are sort of the test cases that sort of give you a hint that you're missing something and you should think for yourself. If we just reveal the private test cases, it kind of defeats the purpose, right? So your tutors should not be giving you the private test cases. They might involve hints, and maybe your tutor can use that to sort of like hint at you what you're missing out on, but in general, we will not be revealing private test cases. Okay, problem set policies. So one thing to note, now that after week 1 is done, right, hopefully you guys get used to the system. Generally, no resubmissions, right? Because we want our tutors to only grade once. We don't want to overburden them with the grading work because there's going to be a lot of grading that they have to do, right? Almost no unsubmission. Please do not submit until you're ready for it to be graded, right? In extreme cases, let's say maybe you had like a gross misunderstanding of the problem set, stuff like that. Communicate with your tutor. It's at their discretion whether they can unsubmit for you for like to retry the problem set, right? Okay, so one more thing. So if you don't understand what's going on with the problem sets, if you don't get the solutions, or let's say you don't even get the problem, your tutor is there to help you with this, right? If you're confused about something, ask on the forums, ask your tutor, right? Come week 4, when you guys get to meet your tutors, maybe they'll put you into groups, and you guys please feel free to ask them questions. Now, our extension policy. This is at the discretion of our tutors. In general, please don't expect that to be an extension. There should be a good reason for this. Maybe you're not feeling well that week, you have an MC or something, let them know, right? And they might give you a few days for an extension. But the reason why we generally try not to give extensions is because we want you guys to keep pace with the module and for them to keep pace with the grading, okay? Okay, so let's get back to algorithms and talking about how to search, right? So last time we talked about binary search. We talked about how it's very easy to add bugs and stuff like that. And we also talked about how to sort of solve other sorts of problems with it, right? So what I mean by this is that we kind of said, look, it's not just for searching values in an array. If you have some kind of like complicated function, but you're promised that the function is monotonic in some way, then we can sort of use binary search to sort of solve our problem, right? So this week, you know, that happened on Monday. But right now, let's just see more examples of this. So let's talk about peak finding. Right? So let's just say, for example, I have an input, which happens to be some function, fx, right? And let's say right now it's not monotonic. But we all agree this is not monotonic, right? If in fact it goes up, it comes back down, so this is definitely not monotonic, right? And let's say right now we want to find local maximums, right? So an example of a local maximum could be this one. That's kind of a local maximum, proof by picture, right? It's also basically the global maximum, right? And I argue that if you have a function for which you want to find the global maximum, that's actually going to be tricky, right? Why? Intuitively speaking, this is not a proof, but intuitively speaking, you kind of have to try the function on all possible inputs, get all of the outputs, plot out this chart, and then kind of find the global maximum. So that might be tricky, right? And even though, let's say, for example, fx is a function you wish to optimize for, maybe this is some sort of utility function, maybe it gives you money or something along those lines. I guess people love money. Maybe this is something you would want to do, right? Typically, this is very hard. So in computer science, we sometimes we can't get this, right? So it's also very common, you might hear in machine learning, that we don't necessarily need global maximums. We'll be happy with local maximums, right? Think of local maximums as like good enough, sane outputs that maybe we want. Take an ML or an AI course, and they might talk a little bit more about this. Yeah, so this is what we're going to try to do today. We're going to try to find local maximums. I'm going to give it the name peak. So we're going to try to do peak finding, right? So in general, finding global maximums is sort of like an optimization problem, and I don't know how many of you like playing RPG games like Path of Exile and stuff like that. People love making spreadsheets, and they go like, oh, I'm gonna min-max the hell out of my games and stuff. That's kind of like trying to find maximums, right? In some sense, conceptually speaking, right? So usually people love finding global maximums, like I mentioned, because it's just the abstract function. You can save money this way, or maybe you can like optimize like some sort of output this way. This is typically stuff we want to find, right? But let me try to sort of sell you on like the fact that maybe it's kind of difficult and why we should settle for local maximums, right? Sometimes for certain problems, we might settle for good enough solutions, right? Sometimes local maxima, depending on the problem, might be close enough to the global maximum. And it might actually be a lot faster to look for a local maximum than a global maximum. So let's say you're really pressed for time, right? You don't really have time to find the global maximum. Okay, maybe we'll try to find something not as good, not the best, but maybe good enough, right? So let's think about this, and let me try to be a little bit more formal about what I just said, right? Let's think about the global maximum again. So let's say I give you an array. So we're indexing from 0 to n minus 1. So the last element is at n minus 1. The first element is at 0, right? And right now, the task and the goal is this. I want you to output the global maximum element in the array. Okay? So question. How long do we think this takes? What should the answer be? I'll give you guys like this. Hopefully it's a bit obvious, but I'll give you guys like 10 seconds to think about this. Again, give the tightest bound, yeah? So like if you tell me, oh, technically we can do it in like 2 to the power of n time, is that really the best answer we can give? So what do we think? What do we think the answer is? Like between 1, 2, 3, 4, and 5. What do we think? I see some people giving bunny ears, right? So like it should probably be 2, right? Let's not fixate too much on this, right? So in general, if you want to find the maximum value, go through the entire array, keep remembering what was the maximum you've seen so far. That's what we're doing on line 2, right? And then just iterate through from the second element to the last element, keep remembering the maximum, update that if you need to, pass through the entire array, and then eventually output that answer, right? Except this takes O(n) time. That's way too slow, right? In fact, this is probably something you might look at and say, I came to CS2040S to learn this? Well, of course not, right? It's like the 5th slide, or it's the 14th slide or something, so obviously we have some cool stuff ahead for you, right? So instead of doing that, let's try to instead now output a local maximum. And I'm going to try to sell you on the idea that we can actually do this pretty fast, yeah? Okay, so let's go to peak finding. So first of all, we kind of need, instead of a function, let's make it a bit simpler. Let's say we have an array, right? Functions might be complicated. Let's just say that we have an array and we want to find a local maximum, right? So we're going to define a peak or a local maximum, a peak. Think of them as the same thing for now, right? Think of a local maximum as an element for which it is greater than or equals to its neighbors. Does that make sense? So for example here, 9 is a peak because it's greater than its neighbors, yeah? 11 here is a peak because it's greater than its neighbors. Same for 23. But what about 21? 21, we're going to accept as a peak, even though it only has one neighbor. We're going to say that, look, if you're past the end of the array, we know there's no element to your right. We'll give that to you for free. Does that make sense? Okay. So the green elements, I hope no one's like dark blue, green, colorblind. But yeah. So like like if you are, just look at the arrows. I guess like they're peaks, right? They're local peaks. In some sense, you can also sort of think of it this way. Past the end of the array, we're going to assume that that in front of the 7 and past the 21, they're just like negative infinity. Like for Java, you might write that as minus maxint. Yeah? Oh yeah, why is 7 not a peak? Good point. I heard someone say that. I think it actually indeed is a peak. So yeah. Somehow, the 7 turned into a 2 in the next slide. Okay, good catch. But let's work with this. So usually at the start of algorithm design, one thing you might want to do before you even come up with a smart algorithm, is to think about what the baseline possible solution is, right? Before you even think of anything ingenious or anything that's like really, really smart, why not think about what's the most basic algorithm you can do, and then we try to optimize it from there, right? So I propose this as a baseline algorithm, right, where basically given the input, we just do the same thing, right? We start from the front, we iterate to the back, and we sort of examine every element and check that it's a peak, right? So start from the first element. Is this a peak? Well, I guess now it's 2, it's not 7, right? So it's not a peak, right? We look at 4. This is definitely also not a peak. We look at 9. We check it and realize it's a peak, so we stop there, right? Now, in the worst, I know I have an example here that stops at the third element, but in the worst case, how long do we expect this to take? N, exactly, right? Because we're starting from the front, we might have to go all the way to the back, right? Imagine like an array where it's just values going all the way up, like straight up, right? Okay, so let's think about a simple improvement. And I think I might have spoiled this, right? But we were still talking about binary search. So instead of starting in the front, where should we start? In the middle, right? Okay, like, not surprising at all. Right, so what should we do when we try to start in the middle? Right, I haven't said anything yet. It's just sort of a vague idea of like, oh, let's start in the middle and see what happens, right? So let's think a little bit. Let's say I start in the middle and 6 is my middle element, right? And let's compare it with its neighbors. Right? So between, why do the numbers keep changing? I don't know. All right, so 5, 6, and 23, right? So we compare with its neighbors. First question, is our middle element 6 here? Is it a peak? It's not a peak, right? So what's the reason why it's not a peak? The right element is larger than 6, right? That's the reason why it's not a peak, right? So let's think for a little bit. We know that 6 is not a peak. We should probably recurse on one side. If we want something efficient, we should probably only recurse on one side. Which side should we recurse on? The left side? It's kind of unintuitive to say left, but the left side or the right side? The right side, right? Because if you think about it, the idea is the following. We know 23 is larger, right? So it might be more likely to find a peak on the right side than on the left side. We'll justify this formally later on, right? But just to be clear, right? We know 5 is less than we know that 5 is less than 6. We don't know what the rest of the input looks like, right? Well, I mean, I've shown it to you guys, but the algorithm doesn't know. Right? On the other hand, on the right side, 6 happens to be, why did I write? Sorry. We're testing whether 6 is larger than 23. It turns out that's not the case, right? Because of that, 6 is not a peak. So we should try to recurse on the right side, right? And we should hope to find a peak on this side. Make sense? Okay? One more thing I want you to note, right? Do you notice how when we recurse on the right side, the reason why we did it was because 6 is smaller than 23, right? So I want you to pay special attention to this border. Do you notice how 6 is smaller than 23? That's going to be very important, right? So just remember that. The reason why we recursed on the right side is because 6 is smaller than 23. So in some sense, 23 is sort of our new border element, but it seems to be larger than its element on the left, right? Okay, so basically that's the idea. So let's recurse, right? Let's keep doing the same thing. So let's say that we recurse again, and somehow, wow, we found another value 6, right? This time it has left neighbor 4 and right neighbor 8. Which side should we recurse on? Which side? The right side. Great, right? So let's do that. Okay, so now our middle element happens to be 17, right? And we can check it, and you might realize that that's a peak, right? 17 is larger than its neighbors, so, well, it's not less than its neighbors, right? It's greater than or equals to its neighbors. So we're going to be happy with that and say, okay, we found a peak. Okay, so based on this observation, maybe you're starting to have an inkling of an algorithm. Maybe it should look something like this, right? To find a peak in an array of n elements, what we should do, let's just say we write this out in an idea right now. We might say something like, oh, if our middle element is a peak, then we basically return that index, let's say, right? Otherwise, the reason why it's not a peak is because it must be smaller than one of its neighbors, right? That's the reason why it's not a peak. So it's either the first case is going to be true, where the right element is larger, in which case we're going to recurse on the right side. That's what we did in our example. Or it could be the other way around, right? Where basically our left element is smaller than our middle element, greater than our middle element, so we recurse on the left side instead, right? Okay, well maybe then let's just fill in the code a little bit more and say, okay, so we should make recursive calls like this. Okay, so do we remember what I mentioned during Monday about binary search? How it might be difficult to it might be difficult to implement it correctly, and it might be easy to introduce bugs, right? So, I have a few of those put in here, right? So, for example, let's think of a few things, right? Question 1, you might ask yourself, oh, the arrow is offset. Okay, I have to fix that. But question number 1, let's say, notice here that in our checks, we're using greater than, right? Think for a little bit. Should this be greater than or equals to? right? We should be very careful about these sort of like boundary conditions, right? Is this correct? Should we write greater than or equals to or greater than, right? Think about the definition of a peak. Does that make sense, right? So that's one thing to note. The other thing to note is that there might be an else condition that's missing, right? You might look at code, and this might not be code that you wrote. Well, it's code that I wrote, I guess. And you might think to yourself, okay, well, do these things make sense, right? For specifically these, think about it a little bit. I hope to convince you that it actually does, right? Well, so the answer to the first one is that no, it should still be strictly larger than, because we want to recurse on that half, right? And the missing else condition doesn't have to be there, because remember, the reason why, let's say we skip past the first branch is definitely because we don't have a peak, right? So if we have a peak, the first condition holds, we definitely return. Otherwise, definitely one of these other two conditions work, okay? Okay, so there are still a few bugs here, actually. So the previous ones weren't actually bugs, just to get you to think about it, right? But I deliberately left this in. So should this be n or n minus 1, right? These are very common mistakes that people make in their binary search, right? And remember, I told you guys on Monday when I interviewed, one of my first internship interviews, I bombed out. This was one of the reasons, by the way. The other thing to note is n over 2 correct, right? So if we specified n there to be the size of the array, is n over 2 correct? Should it be n over 2 minus 1? How many elements are we recursing on? Is it n over 2? Is it n over 2 minus 1, right? One thing, the key takeaway at this point, right, is the following. It's nice to have high-level ideas about algorithms, and in fact, that's how most of us start, right? Except when you also want to implement it in code, these things matter. So I'd like you to take sort of a two-step approach next time, like when you design algorithms. First of all, get the high-level idea, right? Once you're convinced that it's kind of correct, I need you to be very careful with how you do indexing and stuff. Does that make sense? Yeah? So think on this like what it should be, right? So, okay, moving on. So let's say that right now we're still on the first half where we want to convince ourselves it's correct. All I've done is given you a sketch of an algorithm. We haven't really thought very carefully about whether it's correct or not, right? So let's think about this a little bit, right? So what we want to do is sort of take our property here and create an invariant out of this. This is something that we mentioned on Monday, right? So we want to sort of argue that if we recurse on the right half, then there exists a peak in the right half, right? The reason why we want to say this is because, I mean, this ties into the correctness of our algorithm, right? If our algorithm has made a choice, okay, we're going to recurse on the right half. Oh, that's very weird to say, but we're going to recurse on the right half, right? We should be guaranteed that when it returns something, that actually is a peak, right? If this statement doesn't hold, we're screwed, right? Okay, so let's think about this a little bit. We want to sort of like argue that, okay, this is going to be like sort of an inductive argument to some degree. I think I'll get 0 marks for this if I submitted this in 12C1S. But here's the sketch, right? We want to argue that if my algorithm, okay, by the way, I should also mention that if you ask me, but Eldon, what about the proof for the left half? It works the same way, just swap right for left, right? And plus for minus. But here's the idea. So let's say we want to argue that if we recurse in the right half, there exists a peak in the right half. How should we do this, right? I'm going to assume for the sake of contradiction, our favorite way of proving stuff, right? Assume for the sake of contradiction that there is no peak on the right half, okay? But we recurse on the right half, right? So what does that mean? We recurse on the right half, so it means that the middle element has to be strictly less than the element to its right. So element on the left is less than middle plus 1. The element at middle plus 1, okay, it's like a lot of words to say at the same time. But we can sort of keep repeating this argument because there are no peaks, right? Because there are no peaks, we should be able to sort of argue something along the lines that we will always sort of be like going to the right incrementally since there shouldn't be peaks, right? Because we know middle plus 1 is not a peak. We know middle plus 1 is greater than middle. So the only way for middle plus 1 to not be a peak, middle plus 2 has to be larger than middle plus 1, right? Rinse and repeat this argument nonstop all the way until we get to the end of the array, right? Since there are no peaks, we should be able to reach the end of the array in the same way. But hey, we derived the contradiction because the last element itself has to be a peak. Do we agree? Does that make sense? Right? Okay, so this is sort of pictorially what I'm trying to say. Assume, for example, let's say that 6 is not a peak, right? So 23 has to be larger than 6. And because 23 is not a peak, that means we need a value like 24. It could be something else, but let's say 24, right? So on and so forth, right? Rinse and repeat that. So in pictorial form, this is what I'm trying to say. Proof by picture, I guess. 0 marks for 12C1S, right? So again, to recap, this is the idea. Okay, so we arrived at a contradiction. right? Since we arrived at a contradiction, we can say, okay, so our assumption for contradiction was wrong, which means there must be a peak in the right half, right? Repeat the argument for the left side. We're not going to go through that, but that's the idea, okay? So we've sort of, very informally, basically proved this, right? We've basically proved something along the lines of, okay, if our algorithm recurses on the right side, there is a peak on the right half, right? Okay, so this is basically just me being a little bit more formal with the math, nothing much to say here. Like this is just for you to sort of like read back when you read the slides without watching the video, hopefully. But that's basically what I said. Okay, so let's say that based on that, we want to propose the following invariant, right? This is the invariant. This is kind of the invariant that we had for binary search, right? We said here let's think of the current. Let's think of this invariant. We want to say that we want to find a value. We want to find peak, and we want to insist that peak is basically in the range begin and end, right, of our array. Okay, so I have a question at this point. Let's say we propose this invariant. Does it work? What do we think? Right? Let's just say I give you this statement in isolation. Right? So basically what I'm trying to ask you is it good enough to use this invariant to prove that the algorithm works? What do we think? Right? So the idea is the following. It turns out that this invariant by itself is not enough. The difference is really subtle, right? The difference is really subtle. But let's see in action. Let's just suppose for a second, another proof by contradiction, I guess, but let's suppose for a second that this was the correct invariant, right? So we want to insist that basically that if I gave you a begin and an end, there's a peak in that in that region. Let's think about where this might go wrong. Okay? So let's say we run our peak finding algorithm, and for whatever reason it returns 15, right? And 15 here happens to be the last element of our range, right? Okay, well, we know it returns 15, so it has to be bigger than 14, so that part is fine, right? But what is one possible issue with this? It depends on what you picked as your values for begin and end, right? So if, for example, you pick something in the middle of the array, it could be the case that your peak finding algorithm sees the element 15 as a border element, as something that's like the end of the range, so it doesn't check the right side, right? And then what happens is that it will just happily return 15 and say, hey, I found you a peak, right? Have fun. But 15 might not be a peak, based on this invariant, right? This proposed invariant that we're giving here. So what's the point of this, right? Think of it this way. When you're trying to argue about correctness for algorithms, there's something really subtle that goes on here. And I think you guys might know this, because usually when we talk about recursion, we have to be very careful to note that when we solve the subproblem, it's like actually a subproblem, right? So based on that invariant alone, which is a very common proposed invariant by students, right? Think of it this way. We need to ask ourselves the question, if the recursive call finds a peak, is it still a peak after the recursive call returns, right? We need to be sure that when the recursive call solves the problem and it gives us an answer, it actually is a solution, right? So it's a very subtle difference. I know it's bordering on pedantry, but basically the idea is the following. If we want to be really careful with how we argue about correctness, we should probably refine our statement to this instead, right? We want to argue that there exists a peak in the range begin and end, right? Okay, and we want our algorithm to sort of argue, not every possible begin and end, right? But we basically want to refine the statement by saying every peak in begin and end is a peak in 0 to n minus 1, right? And 0 to n minus 1 here is the entire array. Does that make sense? Right? So how do we sort of use this? Think of it this way, right? And okay, to have these invariants, it sort of ties into how you design the algorithm, right? So let's try to do it this time with the refined statement, right? So think again about, let's say, begin and end, meaning begin starts at 11, and let's just say end starts at 18, right? This was halfway through our algorithm, so our algorithm has already run for a little bit, right? So we're sort of promised a few things actually from the previous call, right? So let's think about it a little bit. If let's say that we've recursed, and right now we have 6 elements to care about, okay, if, hypothetically, our algorithm returns a peak value that is in the middle of the range, something that's not either the first or the last element of the range, right? So again, the example here would be 23, right? That's not on the end. That's not on the edge, right? So let's call that a non-border peak. Well, let's say that our algorithm, we made a recursive call, and it returned us a non-border peak, right? We made a recursive call in begin and end, and it gave us something that was not begin or end. Are we guaranteed that this is a peak? Why, yes. What's the intuition? So when we made the subcall, right, it has definitely seen both sides of that element, right? That proposed peak. That algorithm, when you called it, definitely has seen both sides. So you're guaranteed that when it returns you an element, it definitely is a peak, right? It definitely has made both checks, intuitively speaking, right? On the other hand, the question is the following, right? Like, what happens if it returns something? Like, for example, let's say the setup was that I called begin and end, and again, begin points at 11 and end points at 30, and this time it returns you 30, right? This time, to the perspective of your subcall, it's a bordering element, right? So it only made one check. It checked 30 against 23, right? We still want to argue that when it returns that value, it actually really is a peak, right? So at this point, you kind of have to ask yourself one more thing, right? When it returns that value, now that we're stepping back to the big problem, is it still a peak, right? So how do we argue this? Here's the intuition. The reason why we recursed on this begin and end in the first place was probably because we looked at the right side of the array, right? And at some point, we realized that 30 is actually larger than the element to its right. That's the reason why begin and end, we made this call, this subcall with begin and end set to these values, right? The only reason why we did this was because in our algorithm, we said, hey, look, we found something smaller, so we should recurse on the left side, right? Sorry, we found something larger, so we recurse on the left side, right? So think of it this way. So think of it this way, right? The reason why we even made this call was because we're guaranteed that 17 is smaller than 30. That's why it's safe, right? So when the algorithm returns a value, it doesn't matter whether it's a middle element or if it's a border element. It's always correct. Make sense? Okay, so a lot of text to kind of basically argue what I just argued. But that's the idea, right? Does that make sense? So okay, this sounds super intimidating at this point, but let me just sort of try to TLDR it in the following way. When you want to sort of say that your recursive solution solves problems, think of it in the following way, right? When you recurse, are you giving it a valid instance of the subproblem, a valid sort of carbon copy of your problem, right? The original input, right, was the entire array. Let me try to see if I can get a picture of that. Oh, I gotta scroll really far back. Okay, I gotta scroll really far back. Let's not do that. Pretend like 2 through 5 is like the original problem, right? In the original problem, the setup was that we promised that everything to the left of 2 is smaller than 2, and everything to the right of 5, the last element 5, is smaller than 5, right? That was the promise, right? So when we call our peak finding algorithm, we are sort of guaranteed that our starting value of 0 and our ending value of, let's say, n minus 1 was definitely the correct range. A peak definitely exists in this range. When we recursed, right, and we recurse on whatever region that might be, for example, let's say the 11 through 15 range, right, we need to promise that everything past the 15 has to be smaller than the 15, right? Well, not everything, but right next to 15, it has to be smaller than 15. We need to be guaranteed that everything behind, not everything, the one element behind 11 has to be smaller than 11. That's the idea, right? Because then we're actually feeding it a carbon copy of our problem, right? We sort of maintain the promise. That's what it means, basically. Okay, so that's the idea. So this is how you basically argue or sort of analyze the algorithm, at least in an informal way. If you want to see a formal definition, we'll move on to 3230 and you'll be more formal about this, right? Okay, so let's say that was the algorithm. The next thing to ask, right, every time we give an algorithm, there's two usual things you need to analyze. The correctness, because the algorithm has to be correct, as well as the running time, right? So let's just say we're convinced about correctness for now. We still have to worry about running time, right? Because it doesn't matter if your algorithm is correct. If it's not efficient, I'm sorry, that's not the point, right? Well, okay, it has to be correct. I'm saying it has to be correct, right? But it also has to be efficient. That's the whole name of the game here, right? We're in the business of correct and fast algorithms. You have to do two things, right? So let's try to analyze the running time, right? Now, again, maybe this looks familiar. Hopefully it does, but let me just show it to you again. Let Tn be the function that we're going to say this is the amount of time it takes me to find a peak in an array of size n, right? We're making one recursive call. So I'm going to say Tn is Tn over 2, right? But not only do we make one recursive call, we have to do some stuff, right? Like, for example, we need to return a value, we need to compare the middle value with its neighbors and stuff like that. That costs time. It's not free, right? So we're going to put a theta 1 there, right? That's just this, okay, this is the cost of our current level of recursion, right? And Tn over 2 is the cost of whatever the recursive call costs, okay? So there's a few ways to do this, and you'll learn something called, have you guys learned master theorem? No, probably not, right? Okay, so I don't think we're going to flash you master theorem yet. You might see it next semester or next year. But we're going to do it a little informally, right? Again, people who are super rigorous in 1231S might be having a stroke right now. But here's how we're going to do it, right? It's super formal. Okay, so here's how we're going to do it. Here's the intuition. How do we unroll the recurrence, right? How are we able to accomplish this math? Let's think of it in the following way. right? So on line 1, I'm just going to write down the definition of Tn. Makes sense, right? Okay. On line 2, let's think of the following thing. I have Tn over 2. Can't I just repeat the definition of our recurrence, but for Tn over 2? Right? So to do that, I'll take my Tn over 2, and I'll substitute it for Tn over 4 plus theta 1. Does that make sense? Right? So from line 1 to line 2, I'm basically just replacing Tn over 2 by Tn over 4 plus theta 1. Right? Well, Tn over 4 is also like a recursive term, so I can replace Tn over 4 by Tn over 8 plus theta 1. Does that make sense? I mean, after all, 4 divided by 2 is 8, right? Like, I'm not living on planet Mars or something where math is different, right? But basically, we keep doing that, and my question to you is the following. When do we stop unrolling this recurrence? Like, when does the algorithm stop? I'd like to argue that the algorithm stops when n is equals to 1. Let's say that's the base case, right? I didn't specify then the algorithm. I had no space on the slides. But basically, let's say that our recurrence stops when n is equals to 1, right? Like a single array, it's a peak. Let's just return it, right? So all the way to the second last line, I'm basically saying that we're basically going to unroll this recurrence as many times as we need until we hit n is equals to 1. Okay? Now, at this point, you might ask me, what is T1? Well, you're solving the peak finding problem for an array of size 1. I'd like to say that takes theta 1 time. Right? Does that make sense? It's kind of free, right? I only have one element. What else am I supposed to do? Just return it, right? So we're going to replace T1 by theta 1. Okay? So as a general rule, you can, like, just as a shortcut, next time you see this recurrence, Tx is equals to Tx over 2 plus O1. This is sort of like how you justify it, but that's the idea. Right? Okay? So so this is just me explaining. Okay, so now that we have this recurrence, the next thing you need to ask yourself is how many times do we unroll this recurrence, right? Because the number of theta 1 terms we have all the way at the bottom depends on how many of those we crapped out when we unrolled the recurrence. Does that make sense? Right? So the next thing you need to ask yourself is how many of those theta 1 terms we have. It turns out that's the number of times you can divide n by 2 until you reach 1. Right? Do we all know what that value is? Log n. I don't know why I'm so excited about saying log n, but log n, right? So in case you haven't seen this before, right, the other way of seeing it, instead of dividing, you could multiply the other side. So 2 times 2 times 2 times 2 times 2 times 2 times 2, log n times gets you n. Yeah? And I think I mentioned this on Monday, but if you were spacing out, or if you weren't there on Monday, but you're here now, I always assume that log is in base 2. Computer scientists almost always do this, right? If you're a physicist, sorry, we don't consider you part of our group. So it's always log base 2n. Don't tell the physicists I said that. Yeah, okay. So that's the idea, right? You take this recurrence, you unroll it, and you ask yourself, how many of these theta n terms do we have? There are around, at most, log n many such terms, right? So that happens to be O log n. Good? Okay? Okay, so basically, again, that's sort of like how you solve peak finding. Yeah, okay, so this is a summary of the problem description. Oh, one thing to note, right? So we talked about peaks, and we said that a peak is when it's greater than or equals to its neighbors, right? So very, very commonly, when you're problem solving, the next thing you might want to ask yourself is, what happens if we change the description of the problem? Can we still solve it, right? So for example, what about steep peaks? So let's say that we change the less than or equals to be strictly smaller than. So let's say a peak now, I really want it to be strictly better than its neighbors. You must really be better than your neighbor, right? Sounds like a very Singaporean thing to say. Okay, maybe I shouldn't say that, right? I'll get in trouble. Anyway, so the question now might be, let's say we revise the question a little bit. Let's say we revise the requirement, we revise the problem, the puzzle. Can we still do it in log n time? What do we think? Gut feeling. Eldon's asking, so the answer is probably no, right? Like, we took so much time to cover the greater than or equals to case, so like maybe this wouldn't work. So here's an intuition, right? Intuitively speaking, if let's say I give you a setup that was like this, all 7s and 1 8 and all 7s again, the only peak here is 8. We agree? Right? But if, let's just say, right, we try to start, like, if we looked anywhere else in the array, we don't know where this 8 is, right? I mean, okay, I give you an example where 8 is there, but 8 could be anywhere, right? I could give you any array where 8 is anywhere and everything else is 7. How do we tell, right? You look at some portion of the array, you don't know where the peak is, you can't tell, right? That's kind of the intuition, right? So if I look in the middle, let's just say we try to run our current algorithm. We look at the middle, right? It doesn't really say anything, right? So at this point in time, you might say, okay, what about maybe there's a magical way. Let's just fix the code a little bit, right? Like let's add a else condition. Maybe that'll fix it, right? So the idea is the following. If you try to do this, it is true that, like say for example, you write here, oh, if I found a stiff peak, I return it. Otherwise, do this funny nonsense, right? But you might see how if you try to apply this code on the previous example, it simply doesn't find the value, right? Because if you think about it, now I'm still using strictly greater than, and if in the middle value was 7 and its neighbors are 7, I'm going to fall into the else case. And in the else case, it says if it's a peak, right? So depends on your definition of peak now. If you use the greater than or equals to definition, you'd output the wrong thing. If the definition of peak here is a strict peak, then I don't know what your algorithm is doing either, right? It's not specified, which is an issue, right? Yeah, so maybe to fix this, what you might say is that, okay, you're right, Eldon, the previous code doesn't work, maybe we shouldn't try something efficient, and we should try to do what you said before at the very beginning of today's class, which is to just try to find a baseline algorithm. So let's say we try to fix it to be correct first, right? So let's say that instead of recursing on either side, we have this following line in our code that says, hey, if the middle element that we found happens to be the same as our neighbors, right, the same value as our neighbors, then we recurse on the left and right sides to try to find a peak, right? To try to find a steep peak, right? So let's just say, I mean, this is correct, by the way, but let's just say that we did this, right? And let me tell you for free that it's correct. The next thing to do, what should we do? Like I've told you it's correct. What's the next step? What do we analyze? We go home, have dinner. Nothing to do. Eldon said it's correct, so full marks. But I get the marks, not you guys, right? So the next thing we need to do is analyze it, right? So this time, because we're recursing on both sides, the recurrence looks like this instead. Right? Tn is our running time. We're making 2 recursive calls to arrays of size roughly n over 2. So we will say 2tn over 2. And each time, after we recurse, the amount of work that we have to do at our current level is still 1. Right? So let's try to analyze this instead. In general, it kind of looks like this. And I'm not going to exactly go through the math here step by step again. But the difference here between this analysis and the previous one is that for this guy, you replace the tn over 2 by 2tn over 4 plus 1, so on and so forth. Does that make sense? You're basically unrolling the recurrence again, right? You'll get more practice doing this during the tutorial. I'm going to have to make a video on this, but yes, right? And over there, we'll talk about this in detail, but this is the idea. This is how you would analyze it, right? Okay, one more thing to mention, right? In general, these two, this recurrence and the first one I've shown you, right? My advice is see it once, remember it. You don't have to work it out every time. These are very common recurrences you see in computer science. So the moment you see it, you probably should just eyeball it and say, okay, I know what it is, right? But let me just work out half of it for you. Keep replacing the tn's by substituting the correct terms, right? Eventually, when you unroll the entire thing, you're just going to get something like 1, and then okay, so it'll be like n times t1, n over 2, n over 4, n over 8, n over 16, n over 32, so on and so forth, okay? And if you sort of factor it out very carefully, you can actually argue that this runs in on time. So this sum all the way at the bottom actually sums to on. Okay? Now, I know the slides don't say this, but I'll mention it to you guys. If you want to sort of see how this last line is correct, this last line, right? The reason why it is because of the geometric series. So you know the thing that you learned in high school? Wait, you guys learned geometric series, right? Yes, no, yes, no, yes, right? So you know the thing that you learned in high school when your teachers told you it was useful? They weren't lying to you. It was actually useful. You're using it here. Okay, anyway, that sort of rounds up the analysis for finding steep peaks, right? So in summary, the idea for how to find a peak, not a steep peak, right? That's difficult, right? Is to run binary search. Okay, so at this point you might think to yourself, wow, binary search can solve a lot, right? Can it solve, search for everything? Well, I guess not. It can't really find happiness, right? But instead of trying to find happiness, maybe let's just move on to the second dimension instead, right? We can't find happiness, so let's just settle for something a little better. Okay, so let's move on to 2D. Oh, crap, how do we do this, right? So this time around, let's say I give you a 2D array, and a peak is a value that is not smaller than its 4 neighbors. Okay? Now, by default, if I'm at a corner, I only have to compare against 2 neighbors. Does that make sense? If I'm on the edge, I might only have to compare against 3 neighbors, right? The sides and not the one that run off the edge. Okay? So let's try to find a peak now, right? And of course, the fact that I'm bringing this up now probably means that we want to use this binary search idea somehow, right? So algorithm 1, let's propose the following. Okay, for each column, let's first find the global maximum value. Right? So for example, column 1, the global maximum value here is 7. Column 2, the global maximum value here is 9. Column 3, it's 5. And column 4, it's 5. Yeah? So now that we found like all of the maximums, now let's find the peak, right? So I collect all of the maximums into one array. That's one-dimensional. And now I run the peak finding algorithm. Step 2 is really fast, right? We basically spent all this time painstakingly, I spent all this time painstakingly convincing you it's efficient and that it's correct and everything, right? Okay, so question 1, is this algorithm correct? What do we think? Right? So for example, let's just say that our peak finding algorithm returns us value 9. Right? So 9 here happens to be the peak that we found. Let's just say the peak that we found from this the output of step 2, right? Is it definitely a peak in the 2D array? What do we think? It's a maximum in its column, right? So we know that, like, if we consider like the vertical sort of like comparisons, because 9 is a maximum, it definitely is larger than its values in the column, and because it's a peak in the 1D array, it has to be sort of like larger than the elements on its side, right? Does that make sense? Here, that's a sketch, right? If I had 2 hours, I'd spend all the time convincing you, but anyway, let's move on. Is this algorithm efficient? What do we think? I'll give you guys like a little bit of time to think about it. That's the important part, right? We need to sort of think of two things. We need to think about whether it's correct. We need to think about whether it's efficient, right? So what do we think? Who thinks this algorithm is efficient? Who thinks this algorithm is not efficient? Who thinks this algorithm is somewhere in between? Like maybe it's efficient, maybe it's not efficient. Okay, so well, the answer is actually no, it's not efficient. Okay, now here's the thing, right? This has actually happened to me before, but like during my PhD, when I tried to design algorithms, they'd be like 3 steps, or like let's say 2 steps here. They'd be like 2 steps. 1 step is insanely efficient, and I'll pat myself on the back and be like, wow, I'm such an algorithms like designer, right? And then I'll find out that the first step itself is really expensive, right? So let's think about it a little bit. Step 2 is great, right? We spent all this time designing a really cool, fancy algorithm that maybe someday you guys will use, right? You'll be like, oh, I know how to find peaks, so let's use it, right? Cool, log m time, right? The problem is that when we try to find the maximums throughout all the columns, how long did that take? You had to run through the entire array anyway. You had to run through the entire 2D array anyway, right? To find the maximum for a column, you had to iterate on the column. You had to do this for all columns. You've literally gone through the entire 2D array. So why not just go do that and output the peak, right? What's this old fancy step 2 doing? Like, you could have just done that directly, right? So the point is, right, that we need to be very careful. Even if one of our steps is super efficient, the complexity of the algorithm is the entire thing, right? So don't forget about that, right? So yeah, okay, sorry, I preempted myself here. We have like slides for that, but okay. So step 2, algorithm 2. Let's say that we try to do something else, right? We say finding maximum of the columns is too expensive. That's the reason why we were bottlenecked, and that's why it was not efficient, right? So it was correct, it wasn't efficient. Let's try to fix the efficiency, right? So let's say you're in denial. This happened to me as well, by the way. Every time I design algorithms, oh, it's not efficient. I'm in denial. It's like, okay, it's okay. We can fix this, right? So let's try to fix it, right? So let's say that we change step 1, right? So step 1 now, instead of finding the maximum, I find a peak, right? We collect the peaks, and then we run the 1D peak finding algorithm, right? So let's think about efficiency first, because we want to fix that, right? So let's think about efficiency first. How long does it take for me to find a peak for a column? If I have n rows, so then, in other words, the column is n large, how long does it take for me to find a peak there? Log n, right? Okay, so if I had to do that for every column, that's going to be m log n, which is a bit better than mn. I hope we can agree on that, right? So maybe this might work, right? We've shaved off mn, and now it's m log n, right? Do we foresee other issues with this? So it might be, it probably is efficient, right? But what other issues must we consider? No issues. Go home, have dinner. Well, it's too early for dinner now, so you have to think about it. Right? So we need to think about correctness, right? And it turns out the algorithm isn't correct. Right? Oh my god, it's like whack-a-mole. You only have like two groundhogs that might pop up, and like when you squish one down, the other one comes up, and you're like, I have 2 hands, how am I missing? Right? Okay, so let's think about this a little bit. Why is this an issue, right? Why is this an issue? Why is it not enough that we find peaks in the columns, right? So I think here we have an example, right? Let's say we take this array 3452, 2125, 1912. Okay, I'm just reading out values at this point. But let's just say that we asked step 1 to find local peaks, right, between the columns, right? So for example, let's say we take the values 3433. Those are peaks for us, right? Those are local peaks. They're not local maximums. We just told the algorithm, I don't care what peak you give me, just give me a peak, right? It might be the maximum value. Who knows? It might not be the maximum value, right? So in this example, we've colored out 3433, right? Okay. Well, at this point in time, let's say that we try to find 1D peaks for this, right? So after on step 2, when we find a 1D peak, we're probably going to report value 4, right? This one, right there. Okay, that wasn't close, but anyway, right there, right? And the issue with that is that if you look back at the original matrix, you'd realize that 4 is more than its neighbor 5. So it's not a global peak, right? And this sort of like brings me back to what I mentioned about how when you make calls like to subproblems and stuff, you need to make sure you're solving the actual problem, right? So like right now, if I found a 1D peak, it's not really solving the actual problem that I want, right? Is it efficient though? Yes, it is, right? So congratulations, you've come up with a really fast algorithm that outputs the wrong answer. I don't know if there are points for that, but I mean, put yourself like 5 years down the road, you're telling your boss, like, you wanted me to do this, right? Like, I did it, it's like really fast. It used to take 2 days, but this program runs in 2 seconds. He goes like, wow, how did you do it? It's like, I output the wrong answer. All right? We can't do that, right? So we have to fix this. We have to fix this, right? Before we go home and have dinner, I mean, you need to make money to buy dinner, right? So we gotta make sure you guys get dinner. So we're gonna have to fix it, right? Okay. So let's sort of like revisit why algorithm 1 worked. It wasn't efficient, but let's think about this a little bit. Why was it helpful, right? Why was it helpful to find the max? When you find the max of the column, you're guaranteed that the vertical comparisons are good, right? When you find the 1D peak, you're guaranteed that in terms of the horizontal comparisons, you're also good, right? For example, take 9. 9 here is the maximum of the column. So you know the up-down comparisons are good. 9 here happens to be larger than 7, and it happens to be larger than 5, which are maximums on their side of the column, right? So when you pick 9, right, you know for a fact that you're larger to the maximums on the columns, like to your left and right? Does that make sense? Yeah? So we really like the maximum. We probably want to make use of this. And the reason why algorithm 2 didn't work, the bait and switch, was because we sort of like threw away that nice guarantee that we had. Okay? We want to make use of this somehow. So let's think about this a little bit. Did we really have to find all the maximums? Right? What do we think? So in algorithm 1, I said find the max elements of all of the columns. Right? And this time now that we're sort of like desperate because we need to make our boss happy, right? Maybe we should reconsider some of the stuff that we did in the algorithm, right? Was it the best choice? Was it important? Was it necessary that we took all of the maximums? What do we think? Eldon's asking, so the answer is probably no, right? Because he's saying think very hard about this, right? So let's think about it this way. Instead of having step 1, where we find the global max for each column, right? Think for a little bit. In step 2, when we try to find the 1D peaks, right, that 1D peak finding algorithm, how many elements do we access, roughly? Log n elements, right? We didn't have to access the entire array, do we agree? We didn't look at all of the elements, we only looked at log n of them, right? So how about, I propose the following, let's try to run the 1D peak finding algorithm, right? And when it needs an element, we compute it. Right? So let's just say that I know we're scratching out step 1, so step 2 is kind of step 1, maybe a bit confusing, I don't know. But let's just try to run the 1D peak finding algorithm, right? And when we try to run that, it's going to want to get a column maximum, right? So let's just say I have a really, really massive array. We can't see the entire thing because, of course, data is always that big nowadays, right? So let's try to do the following. Let's change our algorithm a little bit. Now in step 1, we want to find the max of the middle column. Right? We can do that. So let's just say, hypothetically, our middle column, the maximum value is 10. Right? Let's just say. Right? So now that we found that, we should probably check whether it's a peak, right? Okay? So to do that, after we found the maximum of the middle column, we'll also find the maximum of the columns to its sides. Right? So how many columns do we inspect? 3 columns, right? 3, last I checked, is 01, by the way, so that's kind of good, right? So we have to run through the entire column. That's fine. We're only going through 3 of them. We're not going through all of them, right? So right now, it's like 3n or 3m or something, right? And let's just say that right now, we compare the maximum of these 3 columns, right? So we look at 10, we compare against the maximum of its right column, that happens to be 12. Are we happy? Do we need to recurse? We need to recurse, right? So let's recurse on the right side, and let's say we try the process again. We take another 3 column maximums, right? So in this case, let's say that the maximums were 18, 8, and 14. Do we still recurse? Yes, right? So let's recurse again, right? So let's recurse this time on the right side, because why not? Like both sides are larger, we can pick either side, right? And this time around, we get another 3 column maximums, right? Well, we only need 2 of them, but let's just say 3, it doesn't matter, right? So now this time, 14 happens to be a peak. Are we done? We are, right? We can stop here, right? So at this point in time, let me ask you, how many columns did we use? How many columns did we have to find? Like, how many columns maximums do we need? Did we need all of them? How many do we need? If there are m columns, how many columns do we need to examine, roughly? You can fudge the constants, by the way. I won't sue you. How many do we need? Who thinks the answer is 01? For the whole algorithm, by the way, who thinks the answer is 01? Who thinks the answer is log m? Who thinks the answer is roughly square root of m? Do we need all the columns? That's the most important question. Do we need all the columns? Who thinks yes? Who thinks no? Everyone else not thinking about this, thinking about dinner, right? How do we sell this algorithm, right? Okay, correct. So the answer is log m, right? So what's the idea? What's the intuition here? To round up, right? Algorithm 1 was really nice, right? It said, okay, give me all the maximums around peak finding, it's correct, right? On the other hand, instead of doing that, what we could do is say, I don't need all the maximums. I will compute them whenever I need them, right? So to sort of like summarize the algorithm a little bit, right? Here's the idea. You kind of want to find a peak in the array of maximums, right? So okay, I should have said array of maximums, right? Sorry, we want to find a peak in an array of peaks. This is the original problem. The way to do that is that we want to use the 1D peak finding algorithm, right? When the peak finding algorithm needs a value, only then do we compute it, right? So how do we analyze the running time? Well, the 1D peak finding algorithm needs roughly log m columns, and each column requires O(n) time to find the maximum, right? So the total running time, instead of being O(n)m, is now O(n) log m, right? Space saving, well, not space saving, time savings, right? Ooh, okay, save on a bit of time. Okay, one thing I will mention is that when I was revising these slides from last year, these were from the topics from last year. When I revised it, I actually thought to myself, why are we doing n log m? Don't we have an n plus m algorithm? That's it. That is actually taught in 3230, not in this course, right? It's really cool, but it doesn't use binary search, so that's why we're not covering it now. Yeah, we have optional slides that we will release later this evening. If you're curious about the n plus m, either ask me if you want to know more about it, or you can read the slides yourself. We will cover it there. But in summary, this is kind of like ideas on how you would use binary search. Does that make sense? Yeah? Okay, a few more announcements to make. PS2 is due next week. Hopefully you guys know this. Week 2 lecture training is due tomorrow. And then next week onwards, we're going to talk about sorting. Yay! Okay? Again, week 3 recitations and tutorials will be recorded. I will record it and release it in the later half of the week for week 3. Yeah? Okay. We can end here today. Why do you guys clap? What am I supposed to do? Like that? You guys have been great. Woo!